Hi there. In this video, we want to talk about the paper on the dark side of calibration for modern neural networks. So I thought that in the previous video, we learned about how calibration works in machine learning and classification, especially in binary classification. I thought that this is a good paper published recently, 17 June 2021, and it's showing some of the methods that currently people are using for calibrating the model. And the paper is explaining that when we want to calibrate a deep learning approach, we should care about the calibration and refinement. Refinement is AUC, area under the curve, and indicates the separability of the network correct and incorrect predictions. So they said that regularization-based calibration only focuses on naively reducing a model's confidence. They found that many calibration approaches like label smoothing, manifold mix-up, and etc. lower the utility of the deep neural network by degrading its refinement. So based on the classic knowledge, we know that the calibration shouldn't affect on the AUC and the accuracy of the system. But they're showing that some of these calibration methodology are degrading the refinement and AUC. So as I said in the previous video, that output after a softmax layer of neural network is interpreted as a confidence. And they said that many studies have found that deep neural network output high confidences for incorrectly classified samples. The calibration is not the only component that describes a reliable system. Along with calibration, we also require prediction to be refined or accurate. So they are showing this diagram showing that this is an example that the model is not calibrated and also the refinement is not good. So you cannot have a good separable plane here. Another example is that we have a good refinement, but the calibration is not well. But this one is showing the refinement and calibration, both are good. So the paper focused on a metric called expected calibration error. These common metrics is used like we have the confidences, we have the accuracy, we have number of the total sample falling in bin M, and L is the total sample without considering the bin. So they are saying that the expected calibration error can be calculated by this. And for area under the curve, they are supposing equation 4 that you can see they said that SP and SN are the correct and incorrect classification of model on the test set DT. They try to have a connection between the expected calibration error and this refinement. And after some computation, I don't want to go to much details here, they found this, that we have alpha minus the refinement by a factor beta minus a factor of gamma. So they're saying that if you want to reduce the expected calibration error, we have to reduce alpha or increase the beta. So they said that we can decrease calibration error by either reducing alpha or increasing the R or increasing the AUC. So they're saying that some of the recent methods like the Moon et al. Showed that the refinement-based approach, like improving the AUC, can improve the calibration, but they didn't show how. And they are saying that the reason is that this equation 9. What can we do for decreasing the alpha? We can improve the confidence levels. So changing the confidence levels, changing the logits as the output of the deep neural network. So how the regularization enforces calibration is based on the changing these calibration, changing these logits. So they are showing one of the examples. So we have a way of calibration called entropy regularization. Entropy regularization is like this one. We add a penalty to loss function. So for example, we have a cross entropy loss and we add a penalty to it. And it is entropy regularization. And entropy regularization can be defined as this. So we have the entropy. And by calculating that, if you want to calculate the minimum of this, the paper said that above expression reaches a minimum value when CI is equal to 0.5. This shows that adding entropy regularization will encourage in confidence estimate to be close to 50%, where the entropy is maximum. And for multi-class classification, the minimum is achieved at 1 divided by k. So it means that when we add such regularization, we are enforcing the neurons to 50%. Regularization only helped to tone down the winning class confidence and increase the losing confidence. The improvement in calibration is focused more on the alpha aspect of the equation. So these type of regularization that we added is just working on this part, not on improving the performance of the or AUC of the method. They are changing the calibration, they're changing the confidence levels. And just to elaborate that how entropy regularization can work is that one of the terms that we have is this, that we want to have much of the confidence is near to the 50%, but we have another loss that is trying to have a better discrimination. And there are different type of calibration they mentioned. One is the post-hoc approach that we talked about them in the previous video, like the Platt scattering method that we said, or the beta calibration here, or Dirichlet calibration. There are different type of approaches, like a temperature scaling. This is one of the methods that we didn't talk about. And also there are some methods that have a combination of the regularization and augmentation, not the post-hoc. They said that pre-training and self-supervised learning have also been highlighted to be beneficial for calibration. So what they did is they have different metrics for checking the calibration, like Breyer score, the negative likelihood, the expected calibration error, and overconfidence error. And they have different methods like the temperature scaling and entropy regularization, the label smoothing, the mix-up, and focal loss. They have these different things based on different methods, like the temperature scaling, as we talked about, is here as a post-hoc approaches, or the entropy regularization is a regularization based, or the mix-up is a combination of these augmentation and regularization. So they have different approaches on a dataset CFAR10 and ImageNet, and they try to evaluate how performance in refinement and also the calibration. And they are showing that in this table. So like Breyer score, ECE, this is for calibration, and this is for refinement. So we can see here, like the manifold mix-up is showing the 86%. I think that this is the maximum AUC that we could get. And the lowest ECE and lowest, I guess, Breyer score. But the paper is focusing on something else. One of the important things that they showing is when we apply the calibration, like here we have a baseline, and baseline is like not calibrated. So it's showing the accuracy still is high. Of course, the Breyer score or EC is lower when we apply some of these regularization or calibration method, but the AUC is decreased. So that is the dark side they are focusing on. So they say that if we try to calibrate a method like on this data, so we know that the AUC on the baseline is like 90. When we do the manifold mix-up, the accuracy is decreased. But after data shift, like when I train on this data and test it on another data set, like the baseline here, it was 90 on CFAR10, and when we apply a test, we got 86. And when we apply the calibration, the accuracy is decreased. Of course, the Breyer score and other calibration metrics is lower. But it's saying that applying those calibration or regularization method is decreasing the performance respecting to the baseline. In summary, we can say they have two types of experiments. First is train and testing on one dataset, CFAR10, for example. You can see that the baseline accuracy is high. And while we apply other methods, like the manifold mix-up, the others, the performance is decreased, especially for manifold mix-up. But the calibration errors decreased a little. Maybe this is not something significant. And the more interesting thing is that when we have a new test data and apply the terrain model on that, so we can see the accuracy on baseline decreased a little, but the accuracy on the other, they are decreased. So The reason that we apply the calibration, the first thing is to improving the generalization. But it seems that maybe in some cases, like in this ImageNet that when it's trained by ResNet, we have a baseline of 86, and maybe the manifold mix-up is getting the higher score for that. But for CFAR10, it's not like that. It's decreasing when we apply the manifold mix-up. So they are just showing in this paper that the dark side of the calibration is that we should care about the refinement too, especially when data shift happen. And the reason that we apply the calibration is to improve the generalization, but it is not achievable in some cases in deep neural network. So they have some codes about the focal calibration, the confidnet, and on manifold mix-up, they would have different repository there, and some codes about label smoothing and entropy regularization. And yeah, that's it. Thank you and have a good day.